Guys, so I decided to take a bit of a break from some of the more rigorous proofs that I was planning on presenting. I am going to present them in the upcoming days, though. Some of them include the proof of the chain rule, the mean value theorem, etc. So, in this video, though, I'm going to show you a very nice theorem, which essentially states that continuous functions on compact sets are uniformly continuous. So, as a theorem, you should know that all uniformly continuous functions are also continuous. It's a very straightforward proof, and you can do that one on your own. In the opposite is not true. Not every continuous function is uniformly continuous. You can come up with several examples. For example, the function x squared on its domain, it is continuous, but it isn't uniformly continuous on its domain. And there are several other examples of functions that are continuous but are not uniformly continuous. However, what this theorem says is that if you have a continuous function and you restrict its domain to be a compact set, then on that compact set, the continuous function is also uniformly continuous. So that is the theorem. It is a straightforward proof, which is why I would ask you to pause your videos and see if you can write out the proof of this theorem on your own. So by now, I hope you've attempted this question on your own. So yep, let's begin with the proof. So as I said, the proof is actually quite simple. First of all, let's set up everything. Let S, which is a subset of R to the power of n, be a compact set. It's basically, I'm just rewriting and defining the stuff that I'll be using in the proof. Then let F be a function that maps from S to R to the power of m, be a continuous function. So the plan for this proof is to write a proof by contradiction. That is what I'm going to do. Be a continuous function. So what I'm going to do is assume by contradiction that f is not uniformly continuous. On S. And that just means basically the negation of this statement, which is that there exists an epsilon greater than 0 such that for every delta greater than 0, there exist vectors x and y or points x and y in S such that the norm of x minus y is less than delta and the norm of f of x minus f of y is greater than or equal to epsilon. Right? So what I'm going to do now is basically you can take any epsilon greater than 0. It actually does not matter in this case. And you can derive a contradiction for any epsilon greater than 0. Sometimes in some proofs, in fact, most of the times, whenever there is an existential quantifier, you typically show that there is at least one value of epsilon for which this negation is true. In this case, it turns out that it does not matter what epsilon you take, so you can just take any epsilon greater than 0. So what I'm going to do is I'm going to say fix an epsilon greater than 0, fix any epsilon greater than 0. Okay, so here's the idea behind this. What I'm going to do is I'm going to pick two sequences in S. Let's call them x of k and y of k. And then I'm going to show that under certain restrictions, both x and y will converge to the same value. Let's say they converge to a. And since S is compact, what we know is that, since S is compact and x of k and y of k are then sequences in S, we know that this A must also lie in S. And once we know that, and since we know that f is continuous, we know that f of x will converge to f of a, We know f of y will also converge to f of a because x and y are both converging to a. And what we get over here is f of a minus f of a, which is the zero vector. The norm of the zero vector is 0. And we have a contradiction over here because this statement says that 0 is greater than or equal to epsilon, when in fact we clearly know that epsilon is greater than 0 by our assumption. So that is basically how we will derive the contradiction. Now all we need to do is to figure out those little details. So let's go. So what I'm going to do is I'm going to say consider the sequence delta k, which is a sequence over k's, to be equal to, consider the sequence given by or defined by delta k is equal to 1 over k for every k in n, the set of natural numbers. That is, delta of k is basically the sequence is basically the sequence 1 comma 1 half comma 1/3 and so on. Then, or let's say also, let x of k this is a sequence over k, and y of k be convergent sequences in S. And notice that this is always possible to do because S is a bounded, S is compact, therefore it's closed and bounded. So there, I mean, since it's bounded, there are always convergent sequences in S. And that is just always possible to do. Even if it's not bounded, you can just pick the same point over and over again, and that will give you a convergent sequence. And I mean, you could also be a little bit more rigorous. You can say, well, let x of k and y of k be sequences in S. And then since S is compact, we know that there exist convergent sequences, convergent subsequences of x of k and y of k respectively, whose limit lies in S. You can go ahead and do it that way as well. So I'm gonna emphasize over here that as S is compact, the limit of both these sequences lies in S, and that basically just follows from the Bolzano-Weierstrass theorem. Lies in S. Let limit as k approaches infinity of x of k be equal to the vector A. Then for each k in n, this is something we know is true because of the fact. So here's the idea now. So what I'm saying is now is for each k in n, this condition is satisfied. What we know is that vector x negative vector y will always be less than delta. Now, there is one thing I guess that I should have, I think I should have emphasized on that before, or I should have stated that before. So let me just go back to that real quick. So when I said consider the also let x of k and y of k be convergent sequences in S, and what I forgot to state over here is the fact such that for each k in the set of natural numbers, the norm of x of k minus y of k is less than delta k, or you could say 1 over k. I'm just going to leave it as 1 over k for now. And then I can say that as S is compact, the limit of both these sequences, lies in S. Okay, let me just rewrite this. The limit of both these sequences lies in S. And now I'm basically done. Lies in S. And then we're just going to call that limit A. So let limit as k approaches infinity of x of k be A. Then here's what we know now. As k approaches infinity, we know that the norm of x of k minus y of k approaches 0, because it's always less than 1 over k. So as k approaches infinity, that basically goes to 0. So we know that the norm of x of k minus y of k must also go to 0, because it's positive and it's less than 1 over k. Now, there is one thing that I would like to emphasize before I move on, is the fact that this is always possible to do. Such a sequence is always possible to find, because of the assumption that f is not uniformly continuous, because we know that for every delta greater than 0, it is always possible to find points x and y in S such that the norm of x minus y is less than delta. So this sequence is well defined because of that assumption. Okay, so we know that x of k minus y of k goes to 0, which implies, and this implies, that y of k must also converge, and it should converge to A, because x of k goes to A, and since the norm of the difference of x of k and y of k goes to 0, it follows that y of k must also converge to A. So I should state over here as x of k converges to A. Now, then, as f is continuous, it follows that limit as k approaches infinity of f of vector x or f of x is equal to f of limit as k approaches infinity of, okay, this should be x of k, which is equal to f of A. And similarly, limit as k approaches infinity of f of y of k is equal to f of limit as k approaches infinity of y of k, and this also goes to f of A then, because we know that y of k converges to A. And this of course implies that as k tends to infinity, let limit as k approaches infinity of f of x of k minus f of y of k, this is basically equal to f of A minus f of A, which is equal to the 0 vector, or in fact, better yet, I think I can just finish the proof right here if I just include the norm. So what I should say is that the norm of this is equal to norm of f of A minus f of A, which is equal to 0, and this of course is because remember the second assumption was that this will be greater than or equal to epsilon, but clearly this is not greater than or equal to epsilon. So this is always less than epsilon, or better yet, I should say it's not greater than or equal to epsilon. So that's the first thing. Going back, I guess I should state that A is a vector that lies in S, where A is a vector that lies in S. So that basically completes the proof. This is the proof of the fact that continuous functions on compact sets are uniformly continuous. There are a few things that I would like to emphasize while I'm recapping. So the idea behind the proof comes from the fact that we use this assumption, the first part of the assumption, to create a sequence that such that f of x minus f of y, or yeah, in this case f of x minus f of y is equal to 0, and that means it's not greater than or equal to epsilon, because epsilon by assumption is a number that is greater than 0. So the way we do that is we consider the sequence given by delta equals 1, comma 1/2, comma 1/3, and so on. And then for each one of these terms, we find a sequence we find two sequences such that for each k in the set of natural numbers, x of k minus y of k is less than 1 over k. And these sequences, we can assume that they are convergent. We don't have to. If they are not convergent, we can always pass to a subsequence which actually does converge. So that does not make a big difference. Now, since both of these are convergent sequences in S, by the Bolzano-Weierstrass theorem, we know that their limit also lies in S. So let's call that limit A. So clearly, in this case, what we get is we can even overlook this piece. We know that this will always be satisfied, because we know that as x of k tends to infinity, as k tends to infinity, x of k tends to a, and basically we use this fact and basically we use the fact that the norm of the difference of x and x minus y is less than delta, to conclude that y of k also converges to a. So once we know that both of these converge to A, we can now look at what happens as k tends to infinity of the difference between the norms of f of x, the difference of the norm of the difference of f of x minus f of f of x and f of y. So once we do that, we see that as k tends to infinity, f of x tends to f of a, and then as y tends to infinity, as k tends to infinity, f of y tends to f of a as well. And of course, the f of a minus f of a in this case is just the zero vector. The norm of the zero vector is 0, which can never be greater than or equal to epsilon, because by assumption epsilon was greater than 0. So that is basically the idea behind the proof. There are a few technicalities that you need to be careful with. But yeah, once you've seen the proof, I believe it's fairly straightforward. So yep, that's pretty much it for this video. I hope you enjoyed it. I'll see you in the next video.